Welcome back to the first year topic. We are studying the periodic properties of the elements. Periodic properties of elements. The next periodic property that we consider for the explanation is regarding the ionization enthalpy. Ionization enthalpy. This is indicated as delta IH, or it can also be considered as ionization energy. Ionization energy. It is indicated as IE. The modern concept is enthalpy. The ionization energy is the earlier concept, but both are being considered. When you consider an element in the isolated gaseous state but in the ground state, when such an element, to remove the electron from the such an element to give rise to a positive charged particle, the energy required to remove an electron from the isolated gaseous atom in its ground state is called the ionization energy. Okay, when you consider an atom in its isolated gaseous state, to remove the electron from the outermost orbit, the energy required is called as the ionization energy or ionization enthalpy. Since we are removing the first electron, it can be indicated as IE1. Suppose I take one more electron from this isolated gaseous unipositive ion to give rise to A plus 2. To remove one more electron, the energy required is called as the IE2 or delta IH1, delta IH2. Similarly, for the further removal of the electron, the energy required is called as IE3. IE3. Okay, that is, for the removal of the first electron, energy required is called ionization energy 1. For the second electron, it is IE2. For the third electron, it is IE3. Like that, we can continue. There are some important points to remember on the ionization energy. The first point is, IE is always positive quantity. Is always a positive quantity. In thermodynamics, we will come across energy absorbed is called the energy positive. If energy is released, it is called negative. So anything that is absorbed, anything that is gained, that is positive. Anything that is lost is negative. So ionization energy is actually energy required or absorbed when an electron is to be removed from the outermost orbit, from the isolated gaseous atom. So it is called ionization energy. It is always a positive quantity. If you want, we can write the definition. Energy required to remove an electron. To remove an electron from isolated gaseous atom in its ground state. Ground state. Ground state is actually the state in which the electrons are highly stable or electrons are present in the atom, particular atom. So ionization energy is always positive. The second important point is successive ionization energies. Successive ionization energies are always high. Are always high. That means, that is, IE1 is lesser than IE2, lesser than IE3, etc. This we have to give explanation for this. When we remove one electron from an isolated gaseous atom, the remaining electrons will be held with greater attractive force by the nucleus. That's why the successive ionization energy increases. Second, to remove the second electron, more energy is required as compared to the energy required for the first electron. Since this A plus 2 may be having further attractive force with the nucleus, remaining electrons with the nucleus. So more energy is required for the removal of the third electron. That's why IE1 is lesser than IE2, lesser than IE3. That is, in general, successive ionization energies are always higher. Then the third important point is lower the ionization energy. Lower the ionization energy, higher is the activity or higher is the reactivity of the element. Here is the reactivity of the element. For example, all alkali metals in their particular periods, they are having very low ionization energy. We'll consider the explanation afterwards. But when you consider any element in the first group, comparing to the other elements in the same period, ionization energy will be lower for the first element, that is alkali metal. That's why alkali metals are highly reactive as compared to the other elements. That is, lower the ionization energy, higher will be the reactivity for the particular element. Then these ionization energies or ionization enthalpies depend on various factors. So we can consider factors affecting ionization energy. Factors affecting ionization energy. The first factor is atomic radius. Atomic radius, or we can say atomic size. We know that as we move from across the period, from left to the right across the period, the size gradually becomes smaller and smaller. So as the size becomes smaller and smaller, automatically ionization energy, that is energy required to remove the electron, must increase. So generally when we consider this only as a factor, ionization energy increases across the period. But it is not the only factor. That's why we have to consider second factor. That is, second factor is the electronic configuration. Electronic configuration. It depends on the electronic configuration. That means, if an element is having a stable configuration with the half filled or completely filled, it will be having a higher ionization energy as compared to the other elements. For example, when we consider this 1s2, 2s2, 2p3 for nitrogen atom. Comparing to this nitrogen atom, the previous element is carbon, it is having 1s2, 2s2, 2p2. Just compare. Carbon is having 2p2 configuration, 2s2, 2p2 configuration, while this is having 2s2, 2p3 configuration. Since p orbital is completely half filled, if you write the electrons like this, it is having 2p3 completely half filled configuration. So it gives an extra stability to this configuration, nitrogen atom. That's why to remove the electron from the nitrogen, more energy is required as compared to the carbon. This can also be explained based on the atomic radius. Atomic radius of nitrogen is less as compared to carbon. As the radius is less, it is having the half filled configuration, it is having higher ionization energy as compared to carbon. But when you compare with the oxygen atom is having 1s2, 2s2, 2p4. That means there are 4 electrons in the p orbitals, like this. So 2 electrons in the first and one electron in the second one. Now if you compare the ionization energy of the nitrogen with that of the oxygen, oxygen having 1 extra electron in this 2p can easily lose an electron to have the stable configuration or to get the stable configuration. That's why this oxygen is having lower ionization energy as compared to nitrogen. That is, from carbon to nitrogen there is an increase. From nitrogen to oxygen there is a decrease. But when we go for oxygen to fluorine, fluorine is having lesser radius as compared to fluorine, oxygen. The configuration is 2p5. So it is having one pair in this one and another pair in this one and single electron. Though the electrons are present in the same 2p orbital, the nuclear charge increases, the size decreases. But to remove the electron from this fluorine, more energy is required as compared to that of oxygen. So from oxygen to fluorine, there is an increase in the radius, increase in the ionization energy. That is, when we move across the period, when you consider this atomic radius gradually decreases, as the radius decreases, ionization energy increases. As the second factor, electronic configuration explains, higher the ionization energy for an element having the stable configuration. So from fluorine to fluorine to neon if you move, it is having completely filled configuration, 2s to 2p6. It is highly stable. That's why for the neon, fluorine to neon, there is an increase in the radius. Though the radius gradually decreases, we expect the increase in the atomic ionization energy. It is not regular, there is an irregular variation. At two certain points, there is a decrease. Similarly, if you consider from lithium to beryllium, beryllium to boron, boron to carbon, to nitrogen, to fluorine, and then to neon. Lithium is having 2s1 configuration. Beryllium is having 2s2. Both due to atomic radius as well as electronic configuration, lithium to beryllium there is an increase in the ionization energy. But in this one, it is 2s2, 2p1. So here we have to consider another factor, because the electron is not present in the same orbital, it is present in the 2p orbital. So the third factor that we consider is the type of orbital that is containing the electrons. It is actually called as the penetrating power. Penetrating power. So the third factor is penetrating power. When an electron is present in the s orbital, it is more closer to the nucleus as compared to p orbital. That's why electron present in the p orbital is little away from the nucleus. So we observe that penetrating power of s is more as compared to p, as compared to d, as compared to f. So to remove an electron from the s orbital, more energy is required in the particular shell or orbit. So if all these orbitals contain electrons in the same orbit, then to remove the electron from the s requires more energy than compared to p, than compared to d, than compared to f. That means in the same shell, 2s2, 2p1 configuration, for boron, less energy is required as compared to this beryllium. That's why from lithium to beryllium, increase in the ionization energy. From beryllium to boron, there is a decrease in the ionization energy. From boron to carbon, carbon to nitrogen, there is an increase. Boron to carbon, carbon to nitrogen, there is an increase. But nitrogen to oxygen, there is a decrease. Oxygen to fluorine, fluorine to neon, there is an increase. This is because of the penetrating power, atomic radius and electronic configuration. Then we consider one more factor, that is actually shielding or screening effect. Shielding or screening effect. Suppose you consider a nucleus. This is the orbit, first, second, third, like that. If an electron is present in the outer orbit, this will be having lesser attractive force with the nucleus because of the electrons present in the inner orbits. So these inner orbits prevent the attraction between the outer electron and the nucleus. Thus they act as a screen or shield. So this effect is called as the shielding or screening effect. More the number of electrons in the inner orbits, more will be the screening effect, less will be the attractive force. That's why because of this screening effect, this electron will have the lesser attractive force. That's why to remove this electron, less energy is required. So higher the screening effect. Lesser is the attractive force. And hence ionization energy is less. To remove such an electron, less energy is required. And in this atomic radius we can also include one more factor, that is the nuclear charge. Simple. As nuclear charge increases, automatically attractive force increases. And hence ionization energy increases. This we observe across the period. All these explanations, effect of atomic radius, electronic configuration, that is half filled or completely filled configuration, penetrating power, shielding or screening effect, and then the nuclear charge, can be considered to give the variation in the ionization energy in the periodic table, that we can represent by using the graph. That I will graph I will write little for the second period and third period elements. This graph can be indicated for these two period of elements. So let us consider this y-axis as ionization energy, which is measured in terms of kilojoules per mole. For 1 mole we will consider the ionization energy, that is kilojoules per mole, and this is atomic number. As atomic number increases, we move across the period. So first let us consider this as about 500 kilojoules, 1000, 1500, 2000, 2500. First we consider this atomic number 5, 1 to 5. When we consider this as atomic number 10, 15, 20 like this, then for the first element, hydrogen, with atomic number 1, the ionization energy is around 800 or 900 kilojoules per mole. This is hydrogen. When we move from hydrogen to helium, it jumps like this. Helium. It is around 2200 or 300. Actual value is not required, but variation. For this hydrogen to helium, if you move, it is actually having the configuration 1s1, 1s2. Since the orbit is completely filled up, to remove the electron from helium, more energy is required. But when we move from helium to lithium, that is having 2s1 configuration, comparing to hydrogen, it is present in the extra orbit. That's why comparing to hydrogen, this will be having, lithium is having very low ionization energy. Lithium, atomic number 3 for lithium. From lithium to beryllium there is an increase. From beryllium to boron there is a decrease. As I told you, for beryllium, lithium to beryllium, the electronic configuration is 2s2. Because of the half-filled, completely filled configuration, it is having higher energy. But comparing to this beryllium, boron is having 2s2, 2p1. Penetrating power of P is less as compared to S. That's why boron is having lower energy as compared to beryllium. From boron to carbon, carbon to nitrogen, it is having 2p2 and 2p3. That's why there is a continuous increase. This is carbon, this is nitrogen. From nitrogen to oxygen, it is having 2p4 configuration. Because of the extra electron present in the 2p orbital, it requires less energy. So comparing to nitrogen, the oxygen requires lesser energy. But if you remember, from carbon to nitrogen to oxygen, there is an increase in the nuclear charge. That's why oxygen is having higher ionization energy as compared to the carbon, but less as compared to nitrogen. From oxygen to fluorine, fluorine to neon. Compare helium and neon. Helium is having 1s2 configuration, while this one is having 2s2 2p6. Then when you come to the potassium, potassium is having atomic number 19. Okay, so it is having a lower ionization energy as compared to lithium. Same trend we observe in case of the third period. From potassium to magnesium, magnesium to aluminium, aluminium to silicon, silicon to phosphorus, phosphorus to sulfur, chlorine, then argon. Now as we move from hydrogen to lithium to potassium to rubidium, cesium, etc., the ionization energy becomes lesser and lesser. Similarly, from helium to neon to argon, krypton, xenon, etc., again for the noble gases, there is a gradual decrease in the ionization energy. But similar elements will occupy similar positions in the ionization energy graph. Beryllium, magnesium, boron, aluminium, carbon, silicon, nitrogen, phosphorus, oxygen, sulfur. Like that we can compare the ionization energies. So keeping all these five facts. One is atomic radius, then second one is the electronic configuration, the third one penetrating power, the fourth one shielding or screening effect, then last one nuclear charge. We can explain the variation in the ionization energy across the period and down the group. Down the group, ionization energy gradually decreases, but across the period there is no regular variation because of the half filled, completely filled energy or electronic configuration, as well as the penetrating power, etc. So this is about the topic on the ionization energy. Next topic is electron gain enthalpy, that we consider in the next video. Thank you.